Hey, what's up everyone? Today we're going to be talking about stoichiometry. This is AP Chemistry Unit 4.5 and I made these slides on Christmas, so it's all festive. My goal in this is to show you that not only do you already know stoichiometry, but you've been using it basically your whole life. And so I want to make an analogy to Minecraft. Hear me out. So in Minecraft, in order to make a book, you need 3 pieces of paper and 1 leather. So you can kind of write a chemical reaction for this where you have 3 paper and 1 leather coming together to make a book. Now you could use this reaction to predict the yield of having 24 paper and 8 leather. If you have 24 pieces of paper and 8 leather, how many books are you going to be able to make? That's going to be 8 books. What you've done is you've predicted a yield. And you could do this in reverse. Let's say you wanted to make 12 books. How many pieces of paper and how much leather would you need? Well, you would need 36 paper and 12 leather. So we're going to relate this to chemistry. Let's say you have this reaction where 2 potassium chlorates decompose to form 2 potassium hypochlorite and 3 molecules of oxygen. If I had 10 molecules of potassium chlorite, how many molecules of potassium hypochlorite and how many molecules of oxygen would I form? Well, you would form 10 molecules of potassium hypochlorite and 15 molecules of oxygen. Your reaction here, the stoichiometric coefficients, tell you the ratio of reactants to products. So potassium hypochlorite and potassium chlorate are in a 2:2 ratio. So if you have 10 potassium chlorate, you're going to produce 10 potassium hypochlorite. And oxygen and potassium chlorate are in a 3:2 ratio. So if you have 10 potassium chlorates, you're going to form 15 oxygen molecules. This is what's known as the theoretical yield. And the theoretical yield is the maximum amount of product you can form in a reaction given a certain amount of reactant. So that's exactly what we just did. We were given a certain amount of reactant and we predicted how much product we can make. Now, we did this with molecules. So we had 10 molecules of potassium chlorate. But in reality, using molecules is really inefficient because, how are you going to measure out 10 molecules of potassium chlorate? Instead, what we do is we use mass. So we're going to do this problem where 20 grams of potassium chlorate is heated until it completely decomposes. How many grams of oxygen gas can be produced? Now, using our reaction here, we know that the stoichiometric coefficients tell us that for every 2 molecules of potassium chlorate that you have, you're going to form 3 molecules of oxygen. So since you're given 20 grams of potassium chlorate, you need to somehow use that information to find out how many grams of oxygen gas can be produced. And your first step in most stoichiometric problems is going to be converting mass to moles. Moles, so let's do that first. We know that the molar mass of potassium chlorate is 122.6 grams. So 20 grams of potassium chlorate is, if we divide that by the molar mass, that is 0.163 moles of potassium chlorate. Getting the number of moles is really helpful because now we can relate the stoichiometric coefficients. We know that oxygen and potassium chlorate are in a 3:2 ratio. So if you multiply this number by the ratio, 3 moles of oxygen per every 2 moles of potassium chlorate, you produce 0.245 moles of oxygen. Now, the question asks us how many grams of oxygen gas can be produced. So how do you convert moles to mass? Well, you multiply it by the molar mass. Oxygen, diatomic oxygen, has a molar mass of 32 grams. So if you multiply the number of moles by the molar mass, that'll tell you that we form 7.83 grams of oxygen. Okay, let's continue this Minecraft analogy. Let's say we're gonna stick to this book reaction where 3 paper and 1 leather form 1 book. Let's say you had 60 pieces of paper and 8 pieces of leather. How many books are you gonna form? Well, with our paper, you could form 20 books. But the problem is your leather. You only have 8 leather. And with 8 leather, you can only form 8 books. So although you have a lot of paper, your leather is going to actually determine how much product you can form. And in this case, you're going to form 8 books. In this case, your leather is your limiting reactant. It's the reactant that runs out first during a chemical reaction. So in this case, you're gonna form your 8 books and your 8 leather is gonna be used up, but then you're gonna have a lot of paper left over. You're gonna have 36 pieces of paper left over. So it doesn't matter how much paper you have, your leather is your limiting reactant, therefore it determines how much of your product you can form. We could also flip this. We could say instead of 8 leather, we have 20 leather, and instead of 60 paper, we have 24 paper. How many books can be formed? Well, it's still 8. With your leather, you could hypothetically make 20 books, but with your paper, you can only make 8 books. You only have 24 pieces of paper. So in this case, your paper is a limiting reactant. It's the reactant that runs out first during this, crafting, or we're going to soon relate this to a chemical reaction, but your paper runs out first, so that determines how much product you can form. Let's do an actual problem with this. Let's say you have this reaction where 4 iron atoms react with oxygen or 3 molecules of oxygen to form 2 molecules of ferric oxide. We're told that 279.3 grams of iron is reacted with 96 grams of oxygen to produce ferric oxide. What is the limiting reactant and what mass of ferric oxide is formed? If you want to pause the video and try it out for yourself, feel free to, but let's try it. So first of all, we're told how much of our reactants we have, but having the mass is kind of useless for the actual calculation, so we need to take these masses and convert them to moles. Let's start with the iron first. We know that iron has a molar mass of 55.85 grams, so 279.3 grams of iron divided by that molar mass tells us that we have 5 moles of iron. With 5 moles of iron, how many moles of ferric oxide could you hypothetically form? Well, ferric oxide and iron are in a 2:4 ratio, so if you multiply this number by 2 divided by 4, that tells us that we can produce 2.5 moles of ferric oxide. Let's do the same process for oxygen. We have 96 grams of oxygen, and we know that the molar mass of oxygen is 32 grams, so 96 grams of oxygen divided by the molar mass 32 tells us that we have 3 moles of oxygen. How many moles of ferric oxide can you produce with 3 moles of oxygen? Well, ferric oxide and oxygen are in a 2:3 ratio, so if you multiply this number by 2/3, that tells us that we only form 2 moles of ferric oxide with the amount of oxygen that we have. As you can tell, we produce less of our product using our oxygen than our iron, therefore your oxygen is your limiting reactant. And since it's the limiting reactant, we can only hypothetically make 2 moles of ferric oxide with this setup. So that's our first part. We found the limiting reactant. Now we need to find out what mass of ferric oxide is formed. So since our limiting reactant only allows us to form 2 moles of ferric oxide, that's how many moles of ferric oxide we're going to form. So how do you take moles and convert that to mass? You multiply by the molar mass. Ferric oxide has a molar mass of 159.7 grams. So 2 moles times that molar mass tells us that we form 319.4 grams of ferric oxide. So your limiting reactant is oxygen, and 319.4 grams of ferric oxide is formed. This is basically where our Minecraft analogy stops, because unlike Minecraft, real life is not a game. And real life doesn't always go to your expectation. So if you actually try this reaction, you could hypothetically make 319.4 grams of ferric oxide, but you're actually going to produce less than that. Now, as a chemistry student, if you ever did a lab, the main reason why you might produce less product than you mathematically calculated, the main reason is going to be human error. Like you might mess some stuff up. You might like switching solutions between beakers, you might spill some or whatever. So one of the big reasons is going to be human error. Things in a reaction just aren't perfect because we as humans aren't perfect and we make mistakes. But even if you eliminated all human error, your reactions aren't always 100% efficient. And to look at that, we're going to look at the industrial combustion of natural gas. So the major component in natural gas is going to be CH4 or methane. and you combust that with oxygen to form carbon dioxide and water. Now, in an industrial setting, they're going to minimize human error. There's going to be basically no human error. Everything is industrialized, everything is perfect. And still, this reaction isn't 100% efficient. Why is that? Well, within a reaction, you can have a lot of other side reactions that occur. For example, you could have methane reacting with oxygen, but it combusts incompletely and forms carbon monoxide. And carbon monoxide is a poison. It'll kill you. It has killed many, many people in history. You could also have nitrogen reacting with oxygen to form nitrogen monoxide, and in general, other nitrous oxide or nitrogen oxide compounds. But hold on, you might be asking, where did the nitrogen come from? Well, remember, this reaction is the major reaction that's happening. But whenever you're reacting natural gas with oxygen, you're not really reacting it with pure oxygen. It's just not efficient. What you would do is you would react it with air. And in air is mostly nitrogen. It's like a bit more than 70% of air is nitrogen. So you could have that nitrogen reacting with oxygen to form nitrogen monoxide and other nitrogen oxide compounds. And nitrogen monoxide is not only bad for you, it's bad for the environment, and it's just not a chemical you want to deal with. You could also have sulfur reacting with oxygen to form sulfur dioxide. And again, you're asking, where did the sulfur come from? Well, in natural gas, the major component is methane, but natural gas isn't always pure. And in natural gas, you're going to have a lot of sulfur compounds in it. Those are impurities. You just have to deal with the fact that in real life, there are impurities. Having a 100% pure chemical is really hard, despite what Breaking Bad tells you. So you could have sulfur reacting with oxygen to form sulfur dioxide. And this is one of the major reasons for acid rain. So all these compounds are really, really bad. One more thing I want to make a note about is the fact that there's a delta. That delta means that you need energy for this reaction to occur. And all these reactions need some sort of energy input, but you can imagine if you're doing this in a chamber that's literally designed to produce energy in a like a industrial setting, you're using this reaction to produce energy. And when you have a lot of energy, these reactions can occur. So that's why a lot of these side reactions do occur. And so how do people get around this? Well, in an industrial setting, what you do is you add more air than is necessary. So if you look at this chart here, if you did stoichiometric combustion, meaning you put the exact amount of oxygen in order to combust all your methane, that's actually not as efficient as if you did like 10 or 20% excess air. Having 10 to 20% more air than you really need for the reaction is going to maximize efficiency. It's going to reduce a lot of these side reactions, and overall you have less carbon dioxide emissions because you need to combust less to form the same amount of energy. And so that's what this chart is. It says it shows you how much excess air, and then it tells you your carbon dioxide emissions based on what fuel you have. And so that was kind of just like a practical setting. Let's talk about inefficiencies in general. Reactions are not 100% efficient. And so your theoretical yield was the maximum amount of product that you can produce. Let me just move that. Your theoretical yield is the maximum amount of product you can produce in a reaction given a certain amount of reactant. I should say reactant, my bad. But in reality, what you form is your actual yield. That's the amount of product actually produced in a reaction. And your theoretical yield is always going to be less than, your actual yield is always going to be less than your theoretical yield. And so how do you show how efficient a reaction was? Well, you're going to use percent yield. Your percent yield is the percent ratio of actual yield to theoretical yield. And the way you calculate it is by just dividing your actual yield divided by your theoretical yield times 100%. So let's say you're doing a experiment, and first you're doing a reaction, and you first calculate, I have this amount of reactants, theoretically I make this much product. But you do the reaction and you calculate how much product you have, and that actual yield is less than your theoretical yield. So you can use percent yield to measure how efficient your reaction was. Now, a big thing I want to mention is the fact that your percent yield can never be over 100%. If your percent yield is over 100%, then that means you either did something wrong in calculating your theoretical yield, or you did something wrong in the actual experiment. Your percent yield can never be over 100% because theoretically, you can never have more than your actual theoretical yield. So be careful. If you have over 100%, you did something wrong. And in most settings, basically anywhere, you're not going to get 100%. It's essentially impossible. Something's going to go wrong. Some side reaction is going to happen. Something is going to happen that's going to prevent you from getting 100% yield. So, if you're doing a reaction and you get, 70% yield, that's pretty good, depending on what reaction you're doing, of course. So let's do a problem. We have pentane reacting with oxygen to form carbon dioxide and water. And we're asked to determine the percent yield of the reaction if 38.5 grams of carbon dioxide are formed from burning 1 mole of pentane and 2 moles of oxygen. So we first know that our reaction produces 38.5 grams of carbon dioxide. And so the first thing we want to do is convert that to moles. So 38.5 grams of carbon dioxide divided by the molar mass of 44 grams tells us that we produce 0.875 moles of carbon dioxide. That is our actual yield. So now, in order to find percent yield, we need our actual yield and we need our theoretical yield. So how do we calculate theoretical yield? Well, we're given 2 of our reactants and the amount of moles of each. So we need to figure out which one is the limiting reactant, and the limiting reactant is going to determine how much of your carbon dioxide you can theoretically make. So let's do our 1 mole of pentane first. We have 1 mole of pentane, and we know that pentane and carbon dioxide are in a 1:5 ratio. So if you have 1 mole of pentane and you multiply that by 5, that tells us that with 1 mole of pentane, you could hypothetically form 5 moles of carbon dioxide. Let's look at the oxygen. So 2 moles of oxygen, or carbon dioxide and oxygen are in a 5:8 ratio. So if you multiply 2 moles by 5/8, with our oxygen, we could hypothetically make 1.25 moles of carbon dioxide. And since this number is less than this number, it tells us that oxygen is our limiting reactant, and our theoretical yield is 1.25 moles of carbon dioxide. That's our theoretical yield. We have our actual yield, and we're trying to find percent yield. So remember, percent yield was just actual yield over theoretical yield times 100%. So that's 0.875 moles of carbon dioxide divided by 1.25 moles of carbon dioxide times 100%, and that comes out to 70% yield. 70% yield, whatever. You have 70% efficiency. Not bad. So that's how you calculate percent yield. Now, there's something kind of weird about this question. We're asked to determine the percent yield of the reaction if 38.5 grams of carbon dioxide are formed. But the thing is, carbon dioxide is a gas. So how do you measure the mass of a gas? Usually it's pretty complicated. So you really don't measure the mass of a gas. What you can measure though is volume. And we can use certain techniques to use stoichiometry on gases. And the main thing that you need to know is that at standard temperature and pressure, that's what we call STP, standard temperature and pressure, 1 mole of any gas occupies 22.4 liters. So what is standard temperature and pressure? It is 1 atmosphere of pressure and 0 degrees Celsius or 273.15 Kelvin. That is standard temperature and pressure. And at standard temperature and pressure, 1 mole of any gas is going to occupy 22.4 liters. So let's do one last practice problem. We have 2 hydrogens and 1 oxygen coming together to form 2 water molecules. And all of these are gases. We're asked to calculate the volume of hydrogen at STP needed to form 6 moles of water. If we're trying to form 6 moles of water, how many moles of hydrogen are we going to need? Well, we know that water and hydrogen are in a 2:2 ratio. So if you produce 6 moles of water, you're going to need 6 moles of hydrogen. The question asks us for the volume of hydrogen, and we're told that we're at STP, and we know how many moles we have. So how do you convert between moles and volume when you're at STP for a gas? Well, 1 mole of any gas occupies 22.4 liters. So you could multiply this number by 22.4 liters, and that tells you that you need 134.4 liters of hydrogen gas at STP to form 6 moles of water. And that's it. That is stoichiometry. I hope this video was helpful. I hope you learned something. Thank you for watching, and I'll see you later.